Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at our fifth day of notes dealing with the second half of section 17.3, where we get into weak, strong titrations. So weak, strong titrations in many ways have similarities to strong, strong titrations. We have four regions. We need to understand what species are inside the flask, as well as how to calculate pHs along the way. But doing so is very different with a weak, strong, because as a weak, we have equilibrium. So unlike the previous case, this time we're going to have a conjugate base that affects the pH. Remember before when we had a strong, strong, the conjugate that was formed was inactive. So at the equivalence point, pH was 7. In this case, with a weak strong, remember we have a weak acid. It's going to start out acidic, but we're creating a conjugate base. And when all of the weak acid is gone, we now have the conjugate base present in solution. And that's why at the equivalence point, the pH is going to be greater than 7 with a weak acid strong base titration. Why? Exactly what I just said. You have a conjugate base being created that affects the pH. Now, the other thing is you need to be careful with the choice of indicator. When we had a strong, strong, this big swing at the equivalence point was very, very large, and many different indicators would potentially change in that range. So we could have used phenolphthalein or methyl red, even though they change pHs, or I should say they change colors at very different pHs. But they were both in the area of the strong swing. Now, if you look at a weak acid with a strong base, you can see that the equivalence point is above 7, and therefore something like phenolphthalein would work, but methyl red would be a terrible choice of indicator. So choice of indicators in a weak strong titration, you have to be a little bit more careful with it. Now, at the start, the pH is really determined by the concentration of the weak acid and its Ka. Just like before, we haven't started the titration yet, so all we have in the flask is an acid. The difference is, in this case, it's a weak acid. So we can't get the concentration of the hydronium directly from the concentration of the acid. So it's going to be an equilibrium problem. You're going to find the pH like any weak acid using the initial concentration of the acid and Ka. Technically, it's an icebox problem, but remember, as we saw in chapter 16, whenever we do these problems, we really ended up with the Ka equals x squared over the concentration of the acid minus x, and we neglected x as long as it dissociated less than 5%. So that's what we're going to be doing here, is that same kind of math. So like before, we would take the square root of the Ka times the Ha, and that would give us our value of x, which stood for H3O plus. So before the titration begins, this is what we need to know: the concentration of the weak acid and the Ka to calculate the H3O plus and therefore the pH. Now, the other thing you need to understand is what species are present. At this point in the titration, we don't have any base in there, so all we really have is our weak acid. And remember, weak acids dissociate to a lesser degree, so the major species present is really our weak acid in its molecular form. Yes, we will have very small quantities of its conjugate base, but not very much as a weak acid. So really what we've got is our molecular acid that hasn't dissociated to any great degree. So that's the method of calculating the pH and then what species are present at that point. Now, after that, we start to add our base, and we then start to neutralize our acid, and it becomes its conjugate base. What you need to realize is in this region of the titration before the equivalence point, we have a buffer solution. So we have to do math-wise exactly what we did with our buffer calculations. It's technically a common ion double neglect X type problem. So remember, in region 2, we've got a buffer mixture, and we need to find both the concentration of Ha and A minus because they're in our equilibrium situation in high enough quantity to be relevant. And if you recall, what we've got here is H3O plus is going to equal the Ka times the concentration of our acid over the concentration of our base. Technically, these are both a minus and plus X situation. We neglect both X's. But what we end up with is that's our H3O plus. So taking the negative log of that would give us our pH. And at this region, remember, like any buffer situations, we've got our weak acid and its conjugate base in significant quantities. So that's what we've got here. The other thing we're going to have is the product of our strong base that wasn't involved in the neutralization. So we're going to start to see our spectator ion. If our base was sodium hydroxide, we're going to start to see spectator ions of sodium floating around. So we've got some of our sodium from the strong base. The OH minus from our strong base is completely reacted with the H plus from the acid, so we won't see any of that. But we're still going to have a significant quantity of both the weak acid and its conjugate base that gets formed in the neutralization. So really, you need to know we have three prevalent species here: the weak acid, its conjugate base, and then we also have the cation from the strong base present. Now, one important area in this part of the titration is what's called the half equivalence point. Halfway between the starting and the equivalence point, we have a very special situation when we've perfectly neutralized half of our weak acid into its conjugate base. So we've half neutralized our weak acid, and we've got an equimolar buffer situation. And remember, an equimolar buffer situation, we know the pH equals the pKa. So whatever the Ka of our weak acid is, the negative log of that would give us a point that we could graph. So if you look up here at the graph, notice 50 milliliters was where our equivalence point was. So halfway to 50 at 25, that point, which is right here, halfway between the 20 and the 30, we know what that point is very quickly and easy by just taking the negative log of the Ka. So that's a point that we know that we can plot. And notice it's slowly rising to that point and slowly rising after that point until we get to the equivalence point. So that's a known plot point we can quickly plot in our titration curve. So make sure you know the significance of the half equivalence point in the initial part of our titration here as we start to neutralize the acid. Now, once we have equal amounts of H plus and OH minus, and they've perfectly neutralized each other, in this case, we don't have all spectator ions. We have an active conjugate base that is in the water solution, and that's going to cause the solution here to be slightly basic. So at this point, if we want to calculate the pH, we're going to use the Kb of the conjugate base. So if we had something like acetic acid, we would need the Kb of the acetate anion to calculate the pH. And remember, at this point, we have a base. So when we solve for X, we're going to get OH minus. And remember, it's based upon the Kb of our weak base and its concentration, which remember, we know how many moles of H plus we had. So that means we know exactly how much we need to neutralize. That number of moles divided by the volume would give us the concentration at that point. So it's fairly easy to calculate the A minus concentration because we've perfectly neutralized all of our weak acid. The number of moles that it took to do that divided by the total volume in liters would equal our A minus concentration. Remember, multiply that by Kb, take the square root, and we've got our value for OH minus. Negative log of that, minus 14, would give us our pH. Now, what do we have present at this point? Remember, all of our weak acid is gone. We're going to still have our inactive cation from the strong base floating around. So in this case, if it was sodium hydroxide, we're still going to have Na plus floating around. And now we're going to have our conjugate base. So we really just have A minus and our cation from our strong base floating around in solution. All the H plus and OH minus have neutralized to make water. Now, after the equivalence point, after the big swing, we go back to a steady increase again, just like we saw before the equivalence point. And at this point, we don't have equilibrium math. Really, for the only part of this entire titration, it's after the equivalence point that all we really have is OH minus, and that's a strong base. So this is the excess base region. We've used up all of our weak acid, and while technically we have our weak base there, it becomes irrelevant once we start getting large quantities of OH minus because that's going to be more important than any OH minus that gets created because of the strong base. So really what you're looking at here is how much OH minus was left over. Now remember, the neutralization reaction happens on a particle level, so we need to take the moles of OH minus that we have, so the volume in liters of the base times its concentration, minus the moles of H plus, and remember that's the same as it has been the whole time because we have the same amount of acid in our flask. We subtract those two, but now we're going to have OH minus left over. If we divide that by the total volume in liters, we'd have the concentration of OH minus. Remember, negative log of that subtracted from 14 would give us our pH. And remember, at this point in the titration, we're still going to have some of our weak base floating around, but we're now going to have OH minus in addition to the Na pluses floating around. And yes, we're going to have more Na pluses than the OH minus because remember, they've been accumulating the entire titration. The OH minuses have finally started to appear after the equivalence point. And we're going to have a constant amount of our weak base in solution here relatively. So we also have some of that. And those are really the 4 areas of our titration. Now, one of the things that is a little bit different with a weak strong is you need to understand, is what's in the burette an acid or a base? Because that affects what the pH is going to be at the equivalence point. If we're titrating a weak base with a strong acid, at the equivalence point, our pH is going to be less than 7, and something like methyl red would be a good choice of indicator. But in a weak acid, strong base titration, like we've been talking about, it's going to be greater than 7, so a weak like phenolphthalein as an indicator would be an appropriate choice of indicator. So remember, ideal or indicator should change color at the equivalence point. And for a weak acid strong base, that's going to be greater than 7. So typically something like phenolphthalein would work well, whereas methyl red, perfectly fine for a strong, won't work for a weak acid titrated with a strong base because the color change is going to be before the equivalence point. And you can see here I've superimposed a bunch of different indicators. So there's more than just phenolphthalein that might function well. You have to basically look at the situation and see where the big swing is and what indicator would work well for that. Now, one of the easiest ways to choose is to not really look at that last graph, but to look at the pKa's of our indicators. Remember, our indicators are weak acid that go from undergo a color change when they go to their predominantly acid to their predominantly base form. And that's going to happen around the pKa of the solution. So if your big swing is somewhere between 4.2 and 6.3, something like methyl red would be a great choice. So honestly, easier than looking at the last graph and looking at the color changes is to look at the Ka of the acids, calculate their pKa's, and match that up to the equivalence point. So match the pKa of the indicator with the pH at the equivalence point and choose an appropriate indicator that changes color right around the pH equivalence point. In other words, we're looking for a pKa very similar to pH. So what would be a good indicator for this titration curve? Well, the first thing you have to do is look at, okay, where's our pH in the big swing? Well, right in the middle of it, it's a pH of about 8. So what has a color change right around a pH of 8? Well, phenyl red would be a very good choice for that type of situation. But notice phenolphthalein would probably work as well. And something like bromethymol blue might work because they're all in that big swing. But right in the middle of it, which would be our ideal, would be something like phenyl red. Now, if we're doing a weak acid with a strong base then, and you look at the big picture, remember to know where you're at in the titration. All you really need to do is establish how much H plus and OH minus you have. So how much H plus is in the flask for our acid, and how much OH minus mole-wise have we added from our burette. And by comparing those two, we can see where they're at. When they're equivalent, we're at the equivalence point. If the H plus moles is greater than OH minus, we're before the equivalence point. If we have no H minus, we haven't started the titration yet. And if the H plus is less than the OH minus, we're past the equivalence point. So one of the first things you should always establish, based upon the volumes and the concentrations given, is how many moles of H plus and how many moles of OH minus do we have? Because that's critical to understanding our concentrations and where we're at in the titration. So always establish that up front. Another useful thing to know at the beginning of the titration, and we looked at this yesterday on how you do it, is to calculate the equivalence point volume. So you can actually do a 3-step stoichiometry to actually calculate what is the equivalence point going to be at. And that will help us see where we're at in the titration as well. Now, one of the things that you should know about our equivalence point and what titrations look like for various acids, remember when we have a stronger acid, we're going to get a bigger swing in our equivalence point. When we have a weaker acid, it's going to be a larger pH when we get to the equivalence point, and it's less of a big swing. So the weaker acid, the initial pH is going to be higher, and the pH change near the equivalence point is going to be more subtle. So it gets a little bit trickier to see when you're at the equivalence point when you've got a very weak acid. Now, the pH of the equivalence point, remember, in these titrations is going to be less than 7 because now we're talking about a weak base being titrated with a strong acid. So the weak base is what's in the flask, and a strong acid is now in the burette. So at the very beginning, it's going to be very basic. As we start to add the acid, we're going to slowly neutralize the weak base, and our pH is going to slowly go down. Halfway to the equivalence point, we're still going to get the half equivalence point, but now pKb would equal pH. And then at the equivalence point, we're going to undergo a big swing. But now at the equivalence point, we've used up all of our weak base, and what we have is its conjugate weak acid. So the pH is going to be less than 7 at the equivalence point, and we should choose a indicator appropriately based upon that. Remember, we're looking for a pKa or a pKb for, depending on how it's listed, in the range of our pH at equivalence point. So in this case, the equivalence point is going to be less than 7, so something like methyl red would be a good indicator of choice. And remember, in this case, it's very much like the last one. It's just that at the beginning, we're going to have no H+, so it's all about the Kb expression of our initial concentration of our weak base and the Kb of that base. So X, which would equal OH minus, would equal the square root of Kb times OH minus concentration. So it's just a typical weak base problem. And remember, X is going to be OH minus, not H plus. So take that into account when you're getting the pH at the end. And then as we start to neutralize the OH minus, before the equivalence point, we're still going to have more OH minus than H plus. And you need to calculate the moles of OH minus and the moles of H plus. Remember, OH minus isn't going to change, but as we're adding more acid from the burette, the amount of H plus is going to increase. And in this region, we've got the before the equivalence point buffer situation, but now it's a buffer with a weak base. And to calculate the concentration of that weak base, we need to know how many moles of OH minus, subtract that by the moles of H plus, and divide that by the total volume to get our concentration of OH minus. I should say the concentration of our weak base at this point. And then at the equivalence point, H plus is going to equal OH minus, but now it's going to be a Ka problem because all the weak base is gone and all we have is its weak acid. And then after that, it's going to go to a strong acid because we've got H plus left over. And yes, while there is a weak acid, it's not going to contribute all that much to our pH. So it's really how many moles of H plus are left, divide that by the total volume, and do the negative log of that to get your pH. So it's very similar to the weak acid strong base. But remember, in every step, you're looking at it from the opposite point of view. Now, the last thing I wanted to mention related to titrations is what a titration of a polyprotic acid would look like. For every single hydrogen, you're going to have a big swing for each of the ionizations. So you can see in a triprotic acid like H3PO4, we have 3 big swings. The one that happens right away at the beginning, and then we have H2PO3 being neutralized, and then finally HPO3 2 minus being neutralized. So the number of big swings is going to equal the number of hydrogens in the polyprotic acid. So you're going to have multiple equivalence point when you have a polyprotic acid. And that finishes our second set of notes from section 17.3.